In this video, we're looking at the ratio test, which is one of the final two tests that we'll be doing. The very last one will be the root test. So for the ratio test, what we are looking at here to start off with is sort of, what are some clues, some hints that you should be considering the ratio test when you see a new series. And so looking at this first one, if you try some of the other tests, they're not going to work. And here, when I look at it, I have a mix of two different things. So I have this exponential function, which is similar to a geometric series, but then we have this polynomial term n squared, which makes me think of a p-series. And the mix of these two together is sort of what makes it so I can't really use the comparison test easily here. Okay, so I can't use the comparison test because I have a mix of both p-series and a geometric series. Okay, I have the mix of that polynomial term with the exponential term. So that's one thing that would, sort of give me a hint as to trying the ratio test. The second thing, looking down in this example, this factorial is a big giveaway. Okay, if you have a factorial in your series, then very likely you're going to need to do the ratio test. So having said that, let's go and take a look at what the ratio test is. So here we have the ratio test itself, and we're taking a series, the sum of an, and we're going to be doing a limit on it. We're doing the limit of an plus 1 divided by an. So first off, this might remind you a little bit of the limit we did when we were doing the limit comparison test. In that test, we were doing the limit of an divided by bn, and we wanted to know what happened with that ratio. But there, we were literally comparing the terms from one series to the terms from a second series. Now we are comparing an plus 1 to an. We're comparing the terms in a series essentially to themselves. Okay, we're comparing one term to the previous term. And we want to know what happens with that ratio as n approaches infinity. So as you go infinitely far down the series, what's happening to the ratio of one term to the previous term. And we want to know essentially, is that ratio going to be less than 1, larger than 1, or equal to 1? And based on that, if it's less than 1, we get that our series is going to be convergent. If that limit is larger than 1, we get that our series is going to be divergent. And then, unfortunately, if that limit is equal to 1 exactly, the test fails, the test is inconclusive, you have to go and try a different test. Okay, so those are the three possible outcomes here that we're looking at for the ratio test. And now let's sort of take a little bit more of a look at why the ratio test works the way that it does. We're not going to be doing a full proof here, but we want to develop just a little bit of intuition as to what the test is saying. So first, looking at this, an plus 1 over an, that should actually remind you of something, okay? If you think back to geometric series, okay, for a geometric series, what we were looking at in a geometric series was r, and we looked at the absolute value of r, and we said if that's going to be larger than or equal to 1, then we have divergence. Okay, and if absolute value of r was going to be less than 1, then we ended up with convergence. Okay, so that was sort of our conclusion for a geometric series, and the geometric series, remember, are terms like this. Okay, so fine. Now, what does that have to do with the ratio test? Well, think about how we defined that common ratio r. Okay, remember that r was going to be the ratio of one term to the next term. So if we are looking at the geometric series and we have a plus ar squared and so on, then we remember that going from one term to the next, all that we did was multiply each term by r. Okay, and we wanted to know what the value of r was. Well, because r is the common ratio, I can literally find it by just doing one term divided by the previous term. So for example, I could take the 10th term and divide it by the 9th term. Or I could do here, sort of the second term divided by the first term, and that common ratio would be the same no matter which pairing of terms you took. Now this right here, this is the connection that we're looking for when we're looking at the ratio test then. So in the ratio test, what we are doing is comparing an plus 1 to an. That's exactly the same sort of thing that we were doing with a geometric series, except that the ratio test works on any series, okay? Or it can potentially work on any series, not just series that are formed with exponentials, okay? So we want to know, as we go infinitely far down, as n gets larger and larger, what is happening to this ratio, okay? Do we have something similar happening, similar to what we had with a convergent geometric series? Or do we have something happening here where L is larger than 1, in which case that's going to be a common ratio that would imply divergence, okay? So that's a little bit of the intuition, okay, with why the ratio test works. That's by no means a proof at all, but the idea is that the ratio test is not so different from what we have looked at with geometric series. We're comparing the terms an and an plus 1 to each other, okay, and we want to know essentially what happens to that ratio as n approaches infinity. Now, that sort of takes care of the situation where an plus 1 is a limit that's larger than 1 or less than 1. Okay, however, what happens here at the end? Why is it that the ratio test fails if that limit is exactly 1? So let's just take a quick look at why the test fails. The easiest way is just maybe to consider two different series. So here, let's look at why is the third condition the way that it is. So first off, let's consider the series 1 over n. Okay, so this is a p series, and it's p equal to 1. It's actually the harmonic series. It's divergent. Okay, and now let's take a look at a second one. Here, let's take another p series, not so different. Let's actually just take 1 over n squared. This is p series with p equal to 2, which is larger than 1, and therefore this one is actually convergent. Okay, so we have two different series. One is divergent, one is convergent. But, okay, what we end up with for both of these is that if I check the limit as n approaches infinity of an plus 1 divided by an for both of them, what do I get? So in the first one here, absolute value 1 over n plus 1 divided by 1 over n. I do this limit, and actually I could just simplify it right away. This is the limit of n over n plus 1. That limit's going to be 1. If I do the same thing with 1 over n squared, I have 1 over n plus 1 squared over 1 over n squared. I simplify that, I have the limit as n goes to infinity of n squared over n plus 1 squared, and the limit is again going to be exactly 1. So what we have here then are two different series. Both give a limit with the ratio test of 1, but one series is divergent and one series is convergent. So this is enough evidence to say that if your limit of the ratio test here is going to be 1, the test is inconclusive. Your series could be convergent, it could be divergent, you don't know. You have to go and do something else. Okay, so when you're doing the ratio test, you are very much hoping that your limit is going to be either a number larger than 1 or a number less than 1. Okay, so that's the basic idea, guys, behind the ratio test. We have some idea as to why it works. Now let's actually just go and do some examples together. So here we have our examples, and these are actually the two series that we started with earlier. In the first one, again, you could try your nth term test. Okay, it's not going to work. It's not a p-series directly. It's not going to be a geometric series. You could go and try integral test and so on, but the idea is that the ratio test here is going to work, and it's not actually that much to do. Okay, it's not too time consuming. So we're just going to check a limit, and we're always doing the same limit for the ratio test. It's going to be the limit of an plus 1 over an. And we set them up. We have here n plus 1 squared over 3 to the power of n plus 1. And that's going to be divided by an. Now, rather than divide by an, I'm going to multiply by the reciprocal 1 over an, and that's going to sort of save us some time here. So I multiply by 3 to the n over n squared. Okay, so this is the limit that we are faced with doing, and every time you do the ratio test, your limit is going to seem complicated when you first set it up. Okay, but the idea is that the very first thing you do after setting up your limit should always be the same. Okay, the nature of the ratio test is that you're always going to be able to pair off these similar terms. So what I mean by that is that in the numerator I have n plus 1 squared, and in the denominator I can pair that with its corresponding term n squared. And then I can do the same thing with my 3 to the power of n divided by 3 to the power of n plus 1. Okay, so we just rewrite it a little bit. We group those together. And now, once you have it like this, you're just going to sort of simplify it, and you're going to look at this limit, and you're going to look at this limit sort of separate from each other. Okay, the first one over here, the second one, I can cancel the 3 to the n with 3 to the n plus 1, and that's just going to leave me with 3 to the power of 1. Okay, so I have 1/3 there at the end. And then this one, n plus 1 all squared divided by n squared. There are a few different ways I could go about doing that limit, but probably the nicest way is just to rewrite it n plus 1 over n to the power of 2, multiplied by 1/3 from the second portion, and now this limit is fairly straightforward. This part just goes to 1 squared, this second part is constant, it goes to 1 over 3, and this whole thing then is just going to go to 1 divided by 3. And again, similar to all of the other tests, okay, once you've done your limit, you stop for a second, consider what this means, the fact that we have here 1/3, and we're doing the ratio test, so we want this limit to be a number that is not 1, and specifically we had this limit is less than 1, which means that by the ratio test, this series is going to be convergent. Okay, so here we have our series AN is going to be convergent by the ratio test. And that's it. Okay, we set up our limit, we do it, you see what you get at the end. Is that number going to be less than 1 or larger than 1? And hopefully it's not going to be equal to 1. So now let's take a look at the second example. Here in the second one, we have this factorial, which is sort of why we are considering the ratio test. Okay, that factorial means that it's not p-series, it's not going to be geometric. It also means that the integral test is out because we don't know how to be integrating something that has, x factorial in it. We can't do that. So here, we're really sort of left with the ratio test, but it's a good option. We're going to be setting up here, an plus 1, so that's 2 times n plus 1, divided by n plus 1 factorial, multiplied by the reciprocal, which is n factorial over 2n, and that is our limit that we need to do. Again, it looks like a complete mess, but we start by rewriting everything. We put the similar terms together, so that means we have 2n plus 2 divided by 2n, and we have n factorial divided by n plus 1 factorial. So now there's sort of two different limits you have to know how to do here. The first one, 2n plus 2 over 2n, that's not actually an issue. You could do L'Hopital's rule there. You could factor out an n from the numerator and the denominator. You could use our shortcut looking at the degrees. It's degree 1 over degree 1 and so on. Really what you're going to get is that this part here, this part is not an issue. It just goes to 1. Okay. The second one, however, n factorial over n plus 1 factorial, there's a very specific technique to use, okay? So I'm going to leave that first part alone for now, 2n plus 2 over 2n. The second one, for the factorial, we always do the same thing, okay? We are going to take the larger factorial. In this case, it's going to be n plus 1 factorial. I'm going to take the larger factorial and I'm going to rewrite it in terms of the smaller factorial. So I'm going to rewrite n plus 1 factorial as n plus 1 multiplied by n factorial. I leave the n factorial alone in the numerator, and this works very nicely because now I can just cancel out these n factorials. Okay, and that's always the way that we deal with those limits, and that means that this entire thing is going to be the limit as n goes to infinity, absolute value 2n plus 2 divided by 2n times n plus 1. Okay, and now actually you could do this one a couple ways. Okay, we have this left over. Let's actually go back now. I sort of wish I hadn't expanded that term. What if I had just left that as 2 times n plus 1? Because now we can do something very convenient. We can just cancel out these n plus 1s, and we see that as n goes to infinity, we end up with a constant divided by infinity, so this whole thing is just going to go to 0. And that's a number that exists. It's less than 1. And therefore, this series, an, is going to be convergent by the ratio test. And that's it. It works in just a few minutes. You go through, you do that limit, and in this case, we get that it's convergent. Okay, so those are sort of that's sort of the basic idea behind the ratio test. We've done some easier examples. In the next video, what we're going to do is we're going to take a look at 2 more examples that are definitely going to be a little bit more complicated. There's a bit more going on, but the same idea applies.